Hello everyone, welcome to this Edureka video on Hadoop tutorial for beginners. In this tutorial we will learn the fundamentals of Hadoop and Spark. We will also implement two interesting big data use cases using Hadoop and Spark. What a better way to learn technology than hands-on training, right? So here's the agenda, and this is what you will be learning in today's training. As I already told you, we have two big data use cases that we will study about. First is the U.S. primary election, and the second is the instant cabs startup, much like Uber cabs. We will start with the problem statements of both the use cases and then proceed ahead to learn the big data technologies and concepts in order to solve them. Since we are going to use Hadoop and Spark, we will start with a brief introduction to Hadoop and Spark. Next, we will understand the components of Hadoop in detail, which are HDFS and Yarn. After understanding Hadoop, we will move on to Spark. We will be learning how Spark works and its different components. Then we will go ahead to understand K-means and Zeppelin. K-means is a machine learning algorithm, and Zeppelin is a tool we are going to use to visualize our data. And finally, we will proceed to the solutions of the use cases with demo. So we are all good to go. Let us start with the U.S. primary election use case first. In this use case, we will be discussing about the 2016 primary elections. In the primary elections, the contenders from each party compete against each other to represent his or her own political party in the final elections. There are two major political parties in the U.S., the Democrats and Republicans. From the Democrats, the contenders were Hillary Clinton and Bernie Sanders, and out of them, Hillary Clinton won the primary elections. And from the Republicans, the contenders were Donald Trump, Ted Cruz, and a few others. As you already know, Donald Trump was the winner from the Republicans. So now, let us assume that you are an analyst already, and you have been hired by Donald Trump, and he tells you that I want to know what were the different reasons because of which Hillary Clinton won. And I want to carry out my upcoming campaigns based on that so I can win the favor of the people that voted for her. So that was the entire agenda. So this is the task that has been given to you as a data analyst. So what is the first thing that you will need to do? The first thing you'll do is that you'll ask for data, and you have got two data sets with you. So let us take a look at what this data set contains. So this is our first data set, which is the U.S. primary election data set. So these are the different fields present in our data set. So the first field is state, so we've got the list of the state of Alabama. The state abbreviation for Alabama is AL. We've got the different counties in Alabama like Artuga, Baldwin, Barber, Bibb, Blount, Bullock, Butler, etc. And then we've got FIPS. Now FIPS are Federal Information Processing Standards Code, so this basically means zip code. Then we've got the party, so which we will be analyzing the Democrats only because we want to know what was the reason for Hillary Clinton's win. So we will be analyzing the Democrats only. And then we've got the candidate. And since I told you there were two candidates, Bernie Sanders and Hillary Clinton, so we've got the name of the candidate here and the number of the votes each candidate got. So Bernie Sanders got 544 in Artuga County and Hillary Clinton got 2387. And this field over here represents the fraction of the votes. So if you add these two together, you will get a 1. So this basically represents the percentage of vote each of the candidates got. So let's take a look at our second data set now. So this data set is the U.S. County Demographic Features data set. So the first we will have, again, FIPS in the area name, Artuga County, Baldwin, and different other counties in Alabama and other states also. The state abbreviation, so here it is only showing Alabama, and the fields that you see here are actually the different features. You won't know what this exactly contains because it is written in a coded form, but let me give you an example what this data set contains. Let me tell you that I'm just showing you a few rows of the data set. This is not the entire data set. So this contains different fields like population in 2014 and 2010, the sex ratio, how many females, males, and then based on some ethnicity, how many Asians, how many Hispanic, how many Black American people, how many Black African people, and then there's also based on the age groups, how many infants, how many senior citizens, how many adults. So there are a lot of fields in our data set, and this will help us to analyze and actually find out what led to the winning of Hillary Clinton. So now you have seen our data set. You have to understand your data set. You have to figure out what are the different features or what are the different columns that you are going to use, and you have to think of a strategy or think of how you're going to carry out this analysis. So this is the entire solution strategy. So the first thing you will do is that you need a data set, and you've got 2 data sets with you. The second thing that you'll need to do is to store that data into HDFS. Now, HDFS is Hadoop Distributed File System, so you need to store the data. The next step is to process that data using Spark components, and we will be using Spark SQL, Spark mlib, etc. So the next task is to transform that data using Spark SQL. Transforming here means filtering out the data and the rows and columns that you might need in order to implement or in order to process this. The next step is clustering this data using Spark mlib, and for clustering our data we will be using k-means, and the final step is to visualize the result using Zeppelin. Now, visualizing this data is also very important because without the visualization you won't be able to identify what were the major reasons, and you won't be able to gain proper insights from your data. Now, don't be scared if you're not familiar with terms like Spark, SQL, Spark mlib, k-means, clustering. You will be learning all of these in today's session. So this is our entire strategy. This is what we're going to do today. This is how we're going to implement this use case and find out why Hillary Clinton won. So now let me give you a visualization of the results. So I'll just show the analysis that I have performed, and I'll show you how it looks. So this is Zeppelin, which is in my master node in my Hadoop cluster, and this is where we're going to visualize our data. So there's a lot of code. Don't be scared. This is just Scala code with Spark SQL, and at the end you will be learning how to write this code. So I'm just jumping onto the visualization part. So this is the first visualization that we have got, and we've analyzed it according to different ethnicities of people. For example, in our x-axis we have foreign-born persons, and in the y-axis we're seeing that among the foreign-born people, what is the popularity of Hillary Clinton among the Asians. And the circles represent the highest values. The bigger circle is the bigger counts. So we have made a few more visualizations. So now we've got a line graph that compares the votes of Hillary Clinton and Bernie Sanders together. Again, we have got an area graph also that compares Bernie Sanders and Hillary Clinton votes, and hence we have a lot more visualization. We have got our bar charts and everything finally. We also have state and county-wise distribution of the votes. So these are the visualizations that will help you derive a conclusion to derive an answer, whatever answer that Donald Trump wants from you. And don't worry, you'll be learning how to do that. I'll explain each and every detail of how I've made these visualizations. Now, let us take a look at our second use case, which is the instant cabs use case. Now, there is a cab startup in the U.S. which is called Instant Cabs, and again, since you did a very great job in analyzing the U.S. elections, they have hired you again to solve their problem now. Basically, this company wants to know what is the demand for cabs at which pinpoint location and during which peak hours. And what they want to do is they want to maximize their profit by finding out the beehive points where they can get a lot of pickups and getting their cabs there during peak hours. So this is your second task. So again, the first thing is that you needed a data set. So this is our Uber data set that has been given to you in order to analyze and find out what were the peak hours and how much cabs are expected in those locations during the peak hours. So this is just a date timestamps that represents a pickup time and a pickup date for a particular Uber ride. This is 8 January 2014, and it is around midnight. And then you've got a latitude and longitude. This represents the location of the pickup, and then this is base, which is at TLC base code. So this is like the license number of the driver. So now again, we have to make a strategy of how we're going to analyze this data. So at first, you have got your data set in CSV format. This is your first step, and you've got the data. Then again, the next step is to store the data in HDFS like we did the first time. Again, we have to transform the data because this data set actually is really, really long. It contains a lot of rows and columns, and maybe you don't want to analyze all of them at once, so you will again filter out some of the rows. After it's transformed, to start clustering again in k-means. Now, I'm going to tell you that not to worry. I'll explain k-means from the start and how to do it. And by cluster, we will find out the center points of each cluster, which will represent each of the pickup points or each of the beehive points. So that is why we're performing clusters, in order to find out the cluster centers, which will represent a beehive point where we will be expecting the maximum number of pickups during peak hours. So this is your entire strategy. Now, let me just show you the visualization of this one also, like I did for the US elections. So here's our code again, which is the Scala and the Spark SQL code. Let me just jump directly to the visualization part. So again, this is our x-axis, and we have the count of the number of pickups. In the y-axis, we have the hours, and that is the time and the day, which we have grouped it according to size and the count, which is the number of pickups. So you can see the largest size that you can see here are these ones, and this is found in the 4th cluster, and it is found at the 17th hour, which is around 5 p.m. This is what we found out after we have analyzed and visualized our data set, our Uber data set. And again, I will be talking about how many clusters are to be made and how to make different clusters and how to find everything out. So this is again the visualization of the Uber data set, and then this one represents the location in order to identify the beehive points. Again, we have classified the number of pickups according to the different hours of the day. So we've got the 24 slices over here, and you can see the biggest slice is in the 17th hour and the 16th hour, which is around 4 to 5 p.m. This is the visualization of the data set. Now let's go back to our presentation. Now we have seen what we have to do, but now let's understand what it takes in order to perform all of this. What are the things that you need to be aware of or you need to learn? So here's what you need to learn in order to perform the analysis of the 2 use cases. We will start with the introduction to Hadoop and Spark, and we will understand what is Hadoop and what is Spark, and then we will take a deep dive into Hadoop to understand the different components of Hadoop. For example, the storage unit of Hadoop, which is known as HDFS, and then Yarn, which is the processing unit of Hadoop, and then we will be using different tools like Apache Spark, which could be easily integrated with Hadoop in order to perform a better analysis. And then we will understand k-means and Zeppelin, because we have used k-means clustering in order to cluster our data, and we have used Zeppelin in order to visualize it. And then we will finally move on to the solution of the use cases where we will be implementing it directly. So this is what you need to learn. So let's get started with Hadoop and Spark. We will start with an introduction to Hadoop and Spark. So now let's take a look at what is Hadoop and what is Spark. So Hadoop is a framework where you can store large clusters of data in a distributed manner and then process them parallelly. Then Hadoop has got 2 components for storage. It has HDFS, which stands for Hadoop Distributed File System, and it allows to dump any kind of data across the Hadoop cluster, and it'll be stored in a distributed manner in commodity hardware for processing. You've got Yarn, which stands for Yet Another Resource Negotiator, and this is the processing unit of Hadoop, which allows parallel processing of the distributed data across your Hadoop cluster in HDFS. Then we've got Spark. So Apache Spark is one of the most popular projects by Apache, and this is an open source cluster computing framework for real-time processing, where on the other hand, Hadoop is used for batch processing. Spark is used for real-time processing, because with Spark, the processing happens in memory, and it provides you with an interface for programming entire clusters with implicit data parallelism and fault tolerance. So what is data parallelism? Data parallelism is a form of parallelization across multiple processes in parallel computing environments. A lot of parallel words in that sentence. So let me tell you simply that it basically means distributing your data across nodes which operate on the data parallel, and it works on fault-tolerant systems like HDFS and S3, and it is built on top of Yarn, because with Yarn you can combine different tools like Apache Spark for better processing of your data. And if you see the topology of Hadoop and Spark, both of them have the same topology, which is a master-slave topology. So in Hadoop, if you consider in terms of HDFS, the master node is known as the name node, and the working node or the slave nodes are known as DataNode. And in Spark, the master is known as master and slave are known as workers. So these are basically daemons. So this is a brief introduction to Hadoop and Spark, and now let's take a look at Spark complementing Hadoop. There's always been a debate about what to choose, Hadoop or Spark, but let me tell you that there is a stubborn misconception that Apache Spark is an alternative to Hadoop, and that is likely to bring an end to the era for Hadoop. It is very difficult to say Hadoop versus Spark because the two framers are not mutually exclusive, but they are better when they are paired with each other. So let's see the different challenges that we address when we are using Spark and Hadoop together. You can see the first point that Spark processes data 100 times faster than MapReduce. So it gives us the results faster and it performs faster analytics. The next point is Spark applications can run on Yarn leveraging Hadoop cluster, and you know that Hadoop cluster is usually set up on commodity hardware, so we are getting better processing, but we are using very low cost hardware. And this will help us cut our cost a lot, so hence also the cheap cost optimization. The third point is that Apache Spark can use HDFS as storage, so you don't need a different storage space for Apache Spark. It can operate on HDFS itself, so you don't have to copy the same file again. And if you want to process it with Spark, so hence you can avoid duplication of files. So Hadoop forms a very strong foundation for any of the future big data initiatives, and Spark is one of those big data initiatives. It has got enhanced features like in memory processing, machine learning capabilities, and you can use it with Hadoop. And Hadoop uses commodity hardware, which can give you better processing with minimum cost. These are the benefits that you get when you combine Spark and Hadoop together in order to analyze big data. Let's see some of the big data use cases. So the first big data use case is web e-tailing. The recommendation engines, whenever you go out on Amazon or any other online shopping site in order to buy something, you will see some recommended items popping below your screen or to the side of your screen. And that is all generated using big data analytics and ad targeting. If you go to Facebook, you see a lot of different items asking you to buy them. And then you got search quality, abuse, and click fraud detection. You can use big data analytics and telecommunications also in order to find out the customer churn prevention, the network performance optimization, analyzing network to predict failure, and you can prevent loss before the error or before the fault actually occurs. It's also widely used by governments for fraud detection and cybersecurity in order to introduce different welfare schemes. Justice, it has been widely used by healthcare and life sciences for health information exchange, gene sequencing, serialization, healthcare service quality improvements, and drug safety. Now let me tell you that with big data analytics, it has been very easy in order to diagnose a particular disease and find out the cure also. So these are some more big data use cases. It is also used in banks and financial services for modeling true risk, fraud detection, credit card scoring, analysis, and many more. It can be used in retail, transportation services, hotels, and food delivery services. And actually, every field you name, no matter whatever business you have, if you're able to use big data efficiently, your company will grow and you will be gaining different insights by using big data analytics and hence improve your business even more. Nowadays, everyone is using big data, and you've seen different fields, and everything is different from each other, but everyone is using big data analytics, and big data analysis can be done with tools like Hadoop and Spark, etc. So this is why big data analytics is very much in demand today and why it is very important for you to learn how to perform big data analytics with tools like this. So now let's take a look at a big data use solution architecture as a whole. You're dealing with big data now. The first thing that you need to do is you need to dump all that data into HDFS and store it in a distributed way. And the next thing is to process that data so that you can gain insights. And we'll be using Yarn because Yarn can allow us to integrate different tools together, which will help us to process the big data. So these are the tools that you can integrate with Yarn. You can choose either Apache Hive, Apache Spark, MapReduce, Apache Kafka in order to analyze big data. And Apache Spark is one of the most popular and most widely used tools with Yarn in order to process big data. So this is an entire solution as a whole. Now, since we have got introduced to Hadoop and Spark, let's take a deeper look at HDFS, which is the storage unit of Hadoop. So HDFS stands for Hadoop Distributed File System, and this is the storage unit for Hadoop. And here is the architecture of HDFS. And since I already told you that it is a master-slave architecture, so the master node is known as NameNode, and slave nodes are known as DataNodes. And then we've got another node here which is known as secondary NameNode. Now don't get confused that secondary NameNode is just going to be a replacement for NameNode, because it is not. So I'll tell you what a secondary NameNode does. So now let's go back and understand the entire architecture properly. So you can see the little icons over all of these different nodes. So basically the NameNode is the master daemon, and you can think of it as the king. Then it's got a helper daemon, which is secondary NameNode, which has the icon of the minister. And then the pawns represent the slave nodes or slave daemons. DataNode over here, it contains the actual data. So whenever you dump a file into HDFS and it gets distributed, your data is stored in the data nodes. The best thing about HDFS is that it creates an abstraction layer over the distributed storage resources. So when you're jumping the HDFS file, it gets distributed in different machines. But you can see the entire HDFS as a single unit because it is laid out in such a structure. Now let us view each of these components one by one. So the first, we will take a look at NameNode. The NameNode is the master daemon, and it contains and manages the data node. So what a NameNode does is it preserves a metadata, and metadata meaning data about data. So whatever file or whatever data is stored in the data nodes, the NameNode maintains a proper sheet, a proper file where everything is mentioned, that what data is stored in which data node, and it serves any kind of request from the clients also. And since it acts as a master node, it's also received heartbeats. The little hearts you saw popping in the earlier slide. The data nodes are actually sending heartbeats to the name node, which is nothing but it just tells the name node what the data node is alive and functioning properly. Now comes the secondary name node. Secondary name node does a very important task, and that task is known as checkpointing. So checkpointing is the process of combining edit logs with FS image. Now let me tell you what an edit log is and what is an FS image. Let's say that I have set up my Hadoop cluster 20 days back, and whatever transactions that happened with every new data blocks are stored in my HDFS. Whatever data blocks are deleted, every transaction is combined in a file known as an FS image. And the FS image resides in your disk. And there's one more similar file which is known as an edit log. Now, edit logs will not keep the record of transactions 20 days back, but just a few hours back. Now, let's say it will keep the record and the transaction details that happen in the past 4 hours, and checkpointing is the task of combining the edit log with an FS image. It allows faster failover as we have a backup of the metadata. So a situation where NameNode goes down and the entire metadata is lost, we don't have to worry. We can set up a new NameNode and get the same transactional files and the metadata from the secondary NameNode because it has been keeping an updated copy, and checkpointing happens after every hour. But you can also configure it. So let's understand the process of checkpointing in detail. Here's the FS image and the edit log. So the FS image in the disk and the edit log resides in your RAM. What the secondary NameNode does is that it first copies the FS image and the edit log and adds them together in order to get the updated FS image, and then this FS image is copied back to the NameNode. And now the NameNode has an updated FS image, and in the meantime, a new edit log is created when the checkpointing is happening. So this process keeps going on, and hence it helps the NameNode in order to keep an updated copy of the FS image of the transactions every hour. Now let's talk about the data nodes. These are the slave daemons, and this is where your actual data is stored. And whenever a client gives a read or write request, the data node serves it because the data is actually stored in the data nodes. So this is all about the components in HDFS. Now let's understand the entire HDFS architecture in detail. So we've got different data nodes here, and we can set up different data nodes in racks. In rack 1, we've got 3 different data nodes, and in rack 2, we've got 2 different data nodes. And each of the data nodes contains different data block because in data nodes, the data is stored in blocks. And so we'll learn about that in the coming slides. So the client can request either a read or write. And let's say that the client requests to read a particular file. It will first go to the name node. And since the name contains the metadata, the name node knows exactly where the file is. So it will give the IP addresses of the data nodes with different data blocks are of that particular file. And it will tell the client that you can go to this IP address and you can go to this data node. And you can read the file, and then the client in turn goes to the different data nodes where the data block is present, and finally the read request is served. And now let's say the client wants to write a file. Again, it will contact the name node and then double click on the metadata, and we'll see where the space is available, and it will check whether space is available or not. And then again, it will give the IP addresses of the data nodes where a client could write the file, and similarly the writing mechanism also happens. So this is how the entire read-write request is served by the data node. Now let's talk about HDFS block replication, and since I've been telling you that HDFS is a fault-tolerant system, let's see how. So each file is stored in HDFS as a block, and whenever you dump a file into HDFS, it breaks down into different blocks, and it is distributed across your Hadoop cluster, and the default size of each block is 128 megabytes. Now let's say I've got a file of 380 megabytes, so it will be divided up into 3 blocks. The first block will be 128 megabytes, the second will be 128 megabytes, and the third will occupy whatever the remaining size of the file, which happens to be 124 megabytes. Now let's say that we have a file size of 500 megabytes. How many blocks will it create? All right, so AJ says it's 4, and Rowett says it's 4. And of course you guys are right, it's 4 blocks. The first 3 blocks will be 128 megabytes, and the last block will just occupy the remaining file size, which is 116 megabytes. So now let's discuss block replication. So whenever you dump your file into HDFS, first it is divided up into blocks, and then each of the blocks is copied 2 times. So now you have the original block and 2 more copies of the same block. So replication factor equal to 3 means that there are 3 similar blocks in your Hadoop cluster. So you can see that I have a file of 248 megabytes, 128 megabytes, and 120 megabytes. So my block 1 is there 3 times, and block 2 is also in there 3 times in 3 different data nodes. So we use this replication factor so that if any of the data nodes goes down, we can retrieve the data block back from the 2 different data nodes. So this is how data blocks are replicated in HDFS. Now, in order to do the replication properly, there's an algorithm which is known as rack awareness, and it provides us optimized fault tolerance. Rack awareness algorithm says that the first replica of a block will be stored in a local rack, and the next 2 replicas will be there in a different rack. So we store a data block in rack 1 so that our latency is decreased. Now these are the commands that you will use to start your Hadoop daemons. Your Hadoop daemons, like your name node, your secondary name node, and your data nodes in the slave machine. So in order to start all the Hadoop daemons in HDFS and Yarn, I have not explained Yarn yet, but Yarn is the processing unit of Hadoop, so it will start all the Yarn daemons like the resource manager and the node manager also. Then this is the command to stop all the Hadoop daemons with JPS. You can check what are the daemons that are currently running in your machine. So let me just show it to you. Now the first thing I need to do is I need to change the directory to my Hadoop directory. So I'll just do cd Hadoop, and now I can run all the commands, and you can remember the first command was /sbin/start all.sh. So it will ask for a password, all right? Now let me tell you that you can also configure it to be a password-less process so that you don't have to enter passwords when it wants to run certain daemons. So now let's use JPS. So here are all the daemons that are running in my master. And I've got my node manager, my secondary name node. JPS itself is a daemon, then DataNode, resource manager, and NameNode. I'll tell you about the resource manager and node manager in the coming slides. Don't worry about that. So these are just the daemons that are running in my master machine. Let me show you what the daemons are running in my slave machine. This is the terminal of my slave machine. I'm just going to run JPS here, and these are the processes or the daemons that are running in my slave machine. So Node Manager and DataNode both are slave daemons, and they are running in my slave machine. If you want to stop all the daemons, you can run the same command, only instead of start, you can just put a stop here. So since I'm going to use my HDFS, I'm not going to stop it and show you, but the process is the same. So these are a few commands that you can use to write or delete a file in Hadoop. If you want to copy a file from your local file system to your HDFS, you use this command, Hadoop fs-put, and this is the name of your file. So you have to type the proper path of the file so that you can copy to HDFS. And you can also mention the destination folder in HDFS where you want to copy it. Now, if you're leaving it blank, it means that it will copy to the master directory in Hadoop. And if you want to list out all the HDFS files, you can do that using this command. If you want to remove that file, remove the same file again, you can use this command, Hadoop fs-rm, which is used for removing. So this is also the first step that you need to do when you're starting to analyze something. And this is the way that you copy your data sets into our HDFS first and then analyze it. So we have seen HDFS. Now let's take a look at Yarn, which is the processing unit of Hadoop. So what is Yarn? Yarn is nothing but it is a MapReduce version 2. So when Hadoop came up with its new version, Hadoop 2.0, it introduced Yarn as the new framework, and it stands for yet another resource negotiator, and it provides the ability to run non-MapReduce applications. And because of Yarn, we are able to integrate with different tools like Apache Spark, Hive, Pig, etc. And it provides us with a paradigm for parallel processing over Hadoop. Now, when you're dumping all your data into HDFS, it is getting distributed, and all this distributed data we are processing in parallel, and it is done with the help of Yarn. And you can see over here that the architecture of Yarn, so that it is again a master-slave topology. So the master daemon here is known as resource manager, and slave daemons are known as node manager. So let's take a look at these components one by one. So first step is the resource manager. So this is the master daemon, and it receives the processing request. And whenever a client comes up with a request, he comes to the resource manager first, because the resource manager manages all the slave nodes or node managers. So whenever a client comes and he wants to process some data, the resource manager takes that request and passes the request to the corresponding node managers. Now, let's see what is a node manager. Node managers are the slave daemons, and they are installed on every data node, so that you know that our data is divided up into blocks and are stored into data nodes, and they are processed in the same machine. So in the same machine where the data node is set, a node manager is also present to process all the data and present in that data node, and it is responsible for the execution of the task on every single data node. So this is where the actual processing of data takes place. Now, let's see the entire architecture in detail. So the client comes up with a request to the resource manager in order to process the data, and then the resource manager passes on the request to the node managers. So they are important components that I'm going to talk about, and you should pay attention to it. So the node manager, we've got a container and app master. Now, an app master is launched for every specific application code or every job or every processing task that the client comes up with. So the application master of the app master is responsible to handle and take care of all the resources that is required in order to execute that code. So if there is any requirement for any resource, it is the app master who asks for the resources from the resource manager, and then the resource manager provides the app master with all the resources, and then it asks the node managers to start a container, and the container is then a place where the actual execution happens. Now let's see the Yarn workflow in order to understand things better. Here is the client, and this client wants to run a job. In this example, I'm considering a MapReduce job, so the MapReduce code is first displayed as MapReduce job, and then the client wants to run this particular job. He submits the job to the resource manager and asks the resource manager to execute this. The resource manager gets back to the client with an application ID for his job. Then the resource manager starts the container where the app master is launched. Now, the app master is also launched in a particular container, and the app master then gathers all the resource requirements in order to run that job and asks the resource manager to allocate all the resources. After that, when all the resources are provided, the node manager launches the container and starts the container. This is where the job executes. Now, let's take a look at the entire Yarn application workflow step by step. So the first step is the client submits an application to the resource manager. Then the resource manager allocates the container to start the app master. Then the app master registers with the resource manager and tells the resource manager that an app master has been created and it is ready to oversee the execution of the code. Then the app master asks containers from the resource manager. The app master also notifies the node manager to launch containers, and after the containers are launched, the application code is executed in the container, which was the application code of the particular client. And then the client contacts the resource manager to ask for the application status, whether it is executed properly or not, or has it been executed successfully. The app master unregisters with the resource manager. So this is the entire workflow. Now let's take a look at the entire Hadoop cluster architecture, HDFS, with Yarn. So here you can see that both HDFS and Yarn follows a master-slave topology, and the master in HDFS is NameNode, and master in Yarn is resource manager. The slave daemons in HDFS are the data nodes, and this is where all your data is stored. And in Yarn, it is node manager. This is where the data is processed in a container, and the app master takes care of all the resources that are necessary in order to execute your program. There is one important thing that you should know, and that you must have noticed, that my data node and my node manager will lie in the same machine. So this data node and this node manager will be in the same machine, and this node manager will be in the same machine, but it is not necessary that the node name and the resource manager would be in the same machine. They could be, but it's not necessary. Now, NameNode can be in a different machine, and a resource manager can be in another machine. All right? So don't get confused that these will not also be in the same machine, which is not the case. Now, let me tell you about the Hadoop cluster hardware specification. Some of the hardware specifics that you should keep in mind if you want to set up a Hadoop cluster. So for the NameNode, you need a RAM with 64 gigs, and your hard disk should be a minimum of 1 terabyte. The processor should be a Xenon 8-core, and the Ethernet should be 3 by 10 gigabytes. The operating system should be 64-bit CentOS or Linux. The power should be redundant power supply because you don't want the NameNode to go down. Why? Because if the NameNode goes down, your entire HDFS will go down, and for the data node, you need 16 gig of RAM. Hard disk should be 6 by 2 terabytes because this is where you will be storing all the data that needs to have a lot of memory. The processor should be Xenon with 2 cores, Ethernet 3 by 10 gigabytes, and OS should be, again, 64-bit CentOS or Linux, and for the secondary NameNode, RAM should be 32 gigabyte. Your hard disk should be 1 terabyte, processor Xenon with 4 cores, Ethernet 3 by 10 gigs, OS should be 64-bit CentOS or Linux, and power again should be a redundant power supply. Now you might pause your screen and take a look at the screenshot of this image. And don't worry, this presentation and this recording will be there in your LMS as well. So this is what you should keep in your mind. It's if you're setting up a Hadoop cluster. So these are the hardware specifications required to do that. Now let me tell you about some real Hadoop cluster deployment. Let us consider our favorite example, which is Facebook. So Facebook has got 21 petabytes of storage in a single HDFS cluster, and 21 petabytes is equal to 10 raised to the power of 15 bytes. And they have got 2,000 machines per cluster and 32 gig of RAM per machine. They run 15 MapReduce tasks, and each of these machines run 15 MapReduce tasks, and 1,200 machines have 8 cores each, and 800 machines have 16 cores each, and there are 12 terabytes of data per machine. So it has got a total of 21 terabytes of configured storage capacity, and it is larger than the previous known Yahoo's cluster, which was known to be the largest Hadoop cluster, and it was 14 petabytes. The Facebook has beaten Yahoo with 21 petabytes. Now let's talk about another use case, which is Spotify. So how many of you listen to music in Spotify? All right, so it looks like some of you do. So even Spotify uses Hadoop for generating music recommendations, because when you listen to music, you see that some of the music, some new songs are recommended to you, which is also belongs to the same genre that you have been listening to, right? So it is done by big data analysis with Hadoop. And Spotify has got 1,650 nodes, and they have 65 petabytes of storage approximately. And Spotify has 70 terabytes of RAM, and they run more than 25,000 daily Hadoop jobs. It's got 43,000 virtualized cores. So it is even larger cluster than Facebook, right? So these were the two use cases who use Hadoop clusters in order to process and store big data. Now that you have learned all about Hadoop, the HDFS, and Yarn, both the storage and the processing components of Hadoop, so let's take a look at Apache Spark. Apache Spark is an open source cluster computing framework for real-time processing, and it has been the thriving open source community and is the most active Apache project at this moment. And Spark components are what make Apache Spark fast and reliable. And a lot of Spark components were built to resolve the issues that cropped up while using Hadoop MapReduce. So Apache Spark has got the following components. It's got the Spark core engine. Now, the core engine is for the entire Spark frameworks. Every component is based on and it is placed in the core engine. So at first, we've got Spark SQL. So Spark SQL is a Spark module for structured data processing, and you can run a modified Hive queries on existing Hadoop deployments. And then we've got Spark Streaming. Now, Spark Streaming is the component of Spark which is used to process real-time streaming data and is a useful addition to the core Spark API because it enables Hive throughput and fault tolerance, stream processing of live data streams. And then we've got Spark MLib. This is the machine learning library for Spark, and we'll be using Spark MLib to implement machine learning in our use cases too. And then we've got GraphX, which is the graph computation engine, and this is the Spot API for graphs and graph parallel computation. It has got a set of fundamental operators like subgraph, join purchases, etc. Then you've got Spark R, so this is the package for R language to enable our users to leverage Spark power from R shell. So the people who have already been working on R are comfortable with it, and they can use R shell directly at the same time, and they can use Spark using this particular component, which is Spark R. You can write all your code in the R shell, and Spark will process it for you. Now let's take a deeper look at realistic people and all these important components. So we've got Spark Core, and Spark Core is the basic engine for large-scale parallel and distributed data processing. The core is the distributed execution engine, and Java, Scala, and Python APIs offer a platform for distributed EDL development, and further additional libraries which are built on top of the core allow for diverse streaming, SQL, and machine learning. It's also responsible for scheduling, distributing, and monitoring jobs in a cluster, and also interacting with storage systems. Let's take a look at the Spark architecture. So Apache Spark has a well-defined and layered architecture where all the Spark components and layers are loosely coupled and integrated with various extensions and libraries. First, let's talk about the driver program. This is the Spark driver, which contains the driver program and Spark context. This is the central point and entry point of the Spark shell, and the driver program runs the main function of the application, and this is the place where Spark context is created. Well, what is Spark context? Spark context represents the connection to the entire Spark cluster, and it can be used to create resilient distributed datasets, accumulators, and broadcast variables on that cluster. And you should know that only one Spark context may be active per Java virtual machine, and you must stop any active Spark context before creating a new one. Let's talk about the driver program that runs on the master knob of the Spark cluster. It schedules the job execution and negotiates with the cluster manager. This is the cluster manager over here, and the cluster manager is an external service that is responsible for acquiring resources on that Spark cluster and allocating them to a Spark job. Then in the worker node, we have got the executors. The executor is a distributed agent that is responsible for the execution of tasks, and every Spark application has its own executor process. Executors usually run for their entire lifetime of the Spark application, and this phenomenon is also known as static allocation of executors, but you can also opt for dynamic locations of executors where you can add or remove Spark executors dynamically to match with the overall workflow. Okay? So now let me tell you what actually happens when the Spark job is submitted. When a client submits a Spark user application code, the driver implicitly converts the code containing transformations and actions into a logical directed acyclic graph, or DAG. And at this stage, the driver program also performs certain kinds of optimizations like pipelining transformations, and then converts the logical DAG into a physical execution of a plan with a set of stages. And after creating a physical execution plan, it creates more physical execution units that are referred to as tasks under each stage. And these tasks are bundled to be sent to the Spark cluster. So the driver program then talks to the cluster manager and negotiates for resources, and the cluster manager then launches the executors on the worker nodes on behalf of the driver. And at this point, the driver sends tasks to the cluster manager based on the day replacement, and before the executors begin execution, they first register themselves with the driver program so that the driver has got a holistic view of all the executors. Now, the executors will execute the various tasks that are assigned to them by the driver program, and at any point in time when the Spark application is running, the driver program will keep on monitoring the set of executors that are running the Spark application code. And this driver program here also schedules future tasks based on data replacement by tracking the location of the cache data. So I hope you have understood the architecture of Spark. Any doubts? All right, no doubts. Now let's take a look at Spark SQL and its architecture. So Spark SQL is the new module in Spark, and it integrates relational processing with Spark's functional programming API, and it supports querying of data either via SQL or via Hive query language. So for those of you who have been familiar with RDBMS, so Spark SQL will be a very easy transition from your earlier tools because you can extend the boundaries of traditional relational data processing with Spark SQL, and it also provides support for various data sources and makes it possible to read SQL queries with code transformation, and that is why Spark SQL has become a very powerful tool. This is the architecture of Spark SQL. So let's talk about each of these components one by one. First, we have got the data source API. So this is the universal API for loading and storing structured data, and it is built on support for Hive, Avro, JSON, JDBC, CVS, Parquet, etc. So it also supports the third-party integration through Spark packages. Then you've got the data frame API. Data frame API is the distributive collection of data that is organized into named columns and is similar to relational table in SQL that is used for storing data in tables. So it is the domain-specific language applicable to, or DSL applicable on structured and semi-structured data. So it processes data from kilobytes to petabytes on a single node cluster to a multi-node cluster, and it provides different APIs for Python, Java, Scala, and R programming. So I hope you have understood all the architecture of Spark SQL. We will be using Spark SQL in order to solve our use cases. So these are the different commands to start the Spark Daemons. These are very similar to Hadoop commands to start the HDFS daemons. So you can see to start all the Spark daemons, so the Spark daemons are master and worker, and you can use this command to check if all the daemons are running on your machine. You can use JPS like Hadoop, and then in order to start the Spark shell, you can use this. And you can go ahead and try this out. So this is very similar to the Hadoop part that I just showed you earlier, so I'm not going to do it again. And then we've seen Apache Spark also. So now let's take a look at k-means and Zeppelin. K-means is the clustering method, and Zeppelin is what we're going to use in order to visualize our data. So let's talk about the k-mean clustering now. K-means is one of the most simplest unsupervised learning algorithms that solves the well-known clustering problem. So the procedure of k-means follows a simple and easy way to classify a data set to a certain number of clusters, which is fixed prior to performing the clustering method. So the main idea is define k-centroids, one for each cluster, and the centroids should be placed in a very cunning way because of different location causes different results. So here, let's take an example. So let's say that we want to cluster a total population of a certain location, And so we want to cluster them into 4 different clusters, namely group 1, 2, and 3, and 4. So the main thing that we should keep in mind is that the objects in group 1 should be as similar as possible, but there should be as much difference between an object in group 1 and group 2. It means that the points that are lying in the same group should have similar characteristics. And it should be different from the points that are lying in a different cluster, and the attributes of the objects are allowed to determine which object should be grouped together. For example, let us take in the same sample that we're using in the U.S. county. So let's consider the second data set we have used. There are a lot of features that I already told you, like there are age groups, and they are categorized by professions, and they also categorized by the ethnicity. And so this is the thing that we are talking about. So these are the attributes that will allow us to cluster our data. So this is k-means clustering. Here is one more example. Let us consider a comparison on income and balance. So in my x-axis, I've got the gross monthly income, and in the y-axis, I have the current balance. I want to cluster my data according to these 2 attributes. Here, if you see, this is my first cluster, and this is my second cluster. So this is the cluster that indicates the people who have high income and low balance in the account, and they spent a lot. And this cluster comprises of the people who have got a low income but a high balance, and they are safe. You can see that all the points that are lying here have got similar characteristics, that they have got low income and high balance. And here are the people who share the same characteristics, where they have got low balance and high income. And there are a few outliers here and there, but they don't form a cluster. So this is an example of k-means clustering, and we'll be using that in order to solve our problems. So does anybody have any questions? So here is one more example and one more problem for you. So you guys will tell me now. So the problem is that I want to set up schools in my city, and these are the points which indicate where each student lives. So my question to you is, where should I be building my school if I have students living around the city in these particular locations? And in order to find that out, we will do k-means clustering, and we'll find out the center point, right? So if you can cluster and make groups of all these locations and set up schools at the center point of each cluster, that would be optimum, isn't it? Because that is how the students have to travel less. It will be close to everyone's house. And there it is. So we have formed 3 clusters. So you can see the brown dots are one cluster, and the blue dots are one cluster, and the red dots are one cluster. And we have set up schools in the center points of each cluster. So here is one, and here is yet another one. So this is where I need to set my schools up so that my students do not have to travel that much. So that was all about k-means, and now let's talk about Apache Zeppelin. This is a web page notebook which brings in data ingestion, data exploration, visualization, sharing, and collaboration features to Hadoop and Spark. So remember, when I showed you my Zeppelin notebook, you can see that we have written the code there. We have even run SQL codes there, and we have more visualizations by executing code there. So this is how interactive Zeppelin is, and it supports many, many interpreters, and it is a very powerful visualization tool that can use, that goes very well with Linux systems, and it supports a lot of language interpreters. It supports R, Python, and a lot of other interpreters. So now let's move on to the solution of the use case. So this is what you've been waiting for. First, we will solve our U.S. county solution. So the first thing we will do is we will store the data into HDFS, and then we will analyze the data by using Scala, Spark SQL, and Spark MLlib. And then finally, we'll find out the results and visualize them using Zeppelin. So this was the entire U.S. election solution strategy that I told you. Now, I don't think I should repeat it again, but if you want me, I can. Should I repeat? All right, so most of the people are saying no, so I will go right through this one again. So let me just go to my VM and execute this for you. So this is my Zeppelin, and I open my notebook here, and let us go to my U.S. election notebook, and this is the code. So first of all, what I'm going to do is that I am importing certain packages because I'll be using certain functions that are in those packages. So I've imported Spark SQL packages, and I have also imported Spark MLlib packages because I'll be using k-means clustering. So vector assembler enables me certain machine learning functions. So over here, I have the vector assembler package that gives me certain machine learning functions that I'm going to use. I've also imported the k-means package because I'll be using k-means clustering. Then the first thing that you need to do is that you need to start the SQL context. So I've started my Spark SQL context here, and the next thing that you need to do is that you need to define a schema, because when you want to dump our data set or we want to dump our data, it should be in a particular format, and we have to tell Spark in which format it should be. So we're defining a schema here. So let me take you through the code. So I'm storing schema in a variable called schema, and we have to define the schema in a proper structure. So we're going to start with struct type, and since you know that our data set has got different fields as columns, we're going to define this as an array of fields. And then this is an array and struct, so we are defining the different fields now. So we'll start with the first field by defining it as struct field inside the braces, which should mention what should be the name of that particular field. So I've named it as state. It should be a string type, and true, that means it is a string type. The next we've got FIPS, which is of string type. Now I know that FIPS is a number, but since we are not going to do any kind of numeric operation on FIPS, we're going to let it stay as a string. Then we've got party as a string type, candidate as a string type, and then votes as integer type, because we're going to count the number of votes, and there's going to be certain numeric operations that we are going to perform that will help us to analyze our data. Then we've got a fraction votes, which you know is a decimal type, so we have to keep it as double type. The next thing you need to do is that Spark needs to read the data set from the HDFS. So for that, you have to use the command spark read, option header true. Header true means that you have mentioned and you have told Spark that my data set already contains column headers, because state as ABBR, they are nothing, but they are column headers. So you don't have to explicitly define the column headers for it. Neither will Spark choose any random row as a column header. So it will choose only the column headers your data set has. Then you have to mention the schema that you have defined. So I have defined it in my variable schema. So that's why I have mentioned it in my file. It should be in CSV format. And then I have mentioned the path of the file in my HDFS. This is the path, and I stored this entire data set in my variable df. Now what I am going to do is that I'm going to divide up certain rows from my data set, because you know that my data set contains both the Republican and Democrat data, and I just want the Democrat data, right? Because we're going to analyze the Hillary Clinton and Bernie Sanders part. Okay, so this is how you divide your data set. So the first thing that we have done is that we have created one more variable called DFR, and we have applied a filter where party is equal to Republican, and then we are storing the Democrat Party data into DFD. So we're going to use the df_d from onwards, and DFR, the Republican data, is going to be your assignment for the next class. Now, I am going to analyze the Democrat data, and then after this class is over, I want you guys to take the Republican data. This data set is already available in your elements, and you've got the VMs, also with everything installed. So please, when you are at home, when you have free time, just analyze the Republican data and tell me what were the reasons that Donald Trump won. I want you to do all that analysis and come up with that in the next class, and we'll discuss about it and whatever results and conclusions that you have made after analyzing the Republican data. And that way you'll also learn even more, and it will also be practice for you after today's class. So all right, so we are going to take df_d now, and the first thing that we will do is that we will create a table view, and I'm going to name the table view as election. Now let me just show you what it looks like and what it has. So this is the command that I have run in Zeppelin. So this is SQL code that I have run in Zeppelin. And you can see that I have got state_ABBR, and I have only got the Democrat data. All right. Now let's go back. All right. So after creating the table view, now all of the Democrat data is in my election table. So now what I'm going to do is that I'm creating a temporary variable, and I'm running Spark SQL code. So what I'm actually doing by writing this code, the motive of writing this SQL code or the SQL query is that I want to refine my data even more. So what I'm trying to analyze here is how a particular candidate actually won. I don't have to do anything with the losing data because you know that each of FIPS contain one of the losing candidate members and one of the winning candidate members. It contains the data of the winning candidate and the losing candidate also because my data set contains both of the data of Bernie Sanders and Hillary Clinton. In some parts, Bernie Sanders won, and in some counties, Hillary Clinton won. So I just want to find out that who are the winners in a particular county, okay? So I'm going to refine that data, and for that I'm using this query. So I'm going to select all from election, and then I'm going to perform an inner join with their query. So this is one more query inside this query, and let me tell you what I'm actually doing. So first of all, what we have done is that we have selected FIPS as B. You know that now you have got two entries for each FIPS, so each FIPS actually appears twice in the data set. So I've named it as B, and now we are counting the maximum fraction votes. So you know that in each FIP we have the maximum fraction vote, and then we can find the winner by actually seeing who has got the maximum fraction votes, and then we have named it as A. The maximum fraction votes column is named as A, and we are grouping by FIPS. So now each of my FIPS will be selected, which has a maximum fraction vote, and I have two columns for that, FIPS, which is 1001 and 1001. So the only row will be selected which has the maximum fraction votes. Now I'll have the winner data, and I've named this entire table inside this query as group TT, and then I'm validating it as where election.fips, the main table view.fips should be equal to the B column that we have created in group TT table, and election.fraction votes should be equal to group TT.A. So any doubts on this query and about how I have written this? All right, so now what we're going to do is that whatever data that we've got here, I'm storing that in election 1. Let me just show you what is in election 1 now. So this is my election table only, and you can see that I've got two FIPS, so 1067, 1067. Now let me show you election 1. So there now I can see that I don't have repetition of FIPS. I have only one entry for FIPS, and that is the row which tells me who won in that county, or in that particular FIP, or in the FIP associated with a particular county. And you can see for Bullock it was Hillary Clinton, for Cahoon it was Hillary Clinton, Cherokee also Hillary Clinton, and then State House District 19 is Bernie Sanders. So Alaska is mainly Bernie Sanders. So this is what we've done now, and then you can see that we have also got additional columns as B and A. So A tells you the maximum fraction votes, and B tells you the FIPS. So the data in FIPS and the data in B are the same, and data in fraction votes and data in A is the same, right? What I'm going to do now is, since my columns are repeating and they have the same value, I don't want A and B now, right? So what I'm going to do is I'm going to filter out the columns I don't need, and in this case I don't want B and A. And what I'm going to do is I'm going to make a temporary variable again, so I'm using the temporary variable to store some data temporarily. So I'm writing to the Spark SQL code to select only the columns that I want. I want the state abbreviation, county, FIPS, party, candidate, votes, fashion votes from election 1. I'm storing everything in dWinner. I've created this new variable, and whatever there was in temp, I'm assigning it to dWinner. And now I've got only the winner data, so I have got all the counties, and I've got who won in that particular county and by how much in the fraction of the votes. What I'm just doing till now is that I'm just refining our data set so that it will be easy for us to make some conclusions or gain some insights from that data, right? And also let me tell you that it's not always necessary that you are filing your data set in the exact way that I'm doing it. If you have something in mind after you've seen your data and understand your data and you found out what actually you need to do, you can carry out different steps to do that also. This is just one way of doing it, and this is my way of doing it. So I'm just telling you, and then we are creating a table for dWinner, and we are going to name it as Democrat. So let me go again and let me show you what the Democrat table view looks like. You can press Shift Enter. So there you we have column A and B that we had in election 1. And so I've just got the winner data. So now let us go back and find out what we're going to find is that I want to find out that which of the candidates won my state, and then whatever date and whatever result I'll get will be stored in the temporary variable when I'm assigning everything. That will be stored in the temporary variable to a new variable called dState, and then similarly, I'm going to create a table view for dState, which is state. Let me show you what my state table view actually contains. So there it is. So I've got state, Connecticut, Hillary Clinton won 55 counties, Florida, Hillary Clinton won 58 counties. So this is what we've come up to for our first data set. So now let's see what we can do with our second data set that contains all the different demographic features. First thing, again, you have to define a schema, and this time I'm naming that schema schema 1, since you know that we have got almost 54 columns, so I have to define all those 54 columns also. So you remember what each of those columns contains. So this is exactly what I have done, and I don't need to go through every line, but like I already told you how to define a schema, you can have the code in your LMS so you can take a look at it. So the next thing we're doing, again, we have to read our data set, and I'm storing my data set into a new variable called df1, and this is the path in my HDFS where my data set was. And then I have created a table view for my data set, which is called facts. Now, let me show you what facts contain. As you can see, that it contains abbreviation, state abbreviation, population 2014. So instead of using the code now, or the encoded form that was actually there in my data set, I have given a varied meta name that would describe what it contains, right? So instead of PST 214, I've got population 2014. So does that make sense? Right. It contains all the 54 demographic features or different features that was in my data set. White alone, not Hispanic or Latino, living in the same house, 1 year and over, foreign-born persons, language or other than English spoken at home, high school graduate or higher. So it contains basically all the different features or all the different columns that actually was in my data set and that I have defined in my schema. So this is what facts I have. So now what I'm going to do is that I'm not going to analyze my whole data based on all these different features. I'm going to choose some specific features in order to analyze it. I'm going to take just a few, add one. So these are the different features that I'm going to use. I'm going to use FIPS, I'm going to use state, I'm going to use state abbreviation, then area name, candidate and people who are over 65 years, senior citizens, female people, white alone, black African alone. I'm choosing Asian alone, Hispanic or Latino. So basically what I'm trying to do is I'm trying to check what is the popularity of Hillary Clinton among the foreign people or people from different ethnicities. So I'm choosing white people, black people, and Hispanic people. So I'm just trying to analyze it, okay? And you know that I have stored this in a temporary variable again, and then whatever result I'll get by running this Spark SQL code, I'll store it in a different variable called dfx, and then I'll store it, and then I'll make a table view for df facts such as winner facts. So let me show you what winner facts look like. So it's winner facts. You've got FIPS, the state is Alabama, the state abbreviation is AL for Alabama. The area name is Artuga County, and the winner was Hillary Clinton, and the people over 65 years in that particular county is 13.8%, female percentage is 51.4%, white alone 77.9%, and so these show you the data. So black, white, or African is 18%, and then I've got the different fields that I have selected. Asian alone, Hispanic or Latino, foreign-born, so I have chosen 14 features to analyze it from. All right? So now what I'm doing again is that I'm going to divide the Hillary Clinton data and the Bernie Sanders data so that we can analyze only why Hillary Clinton won or why Bernie Sanders won in some particular counties. So we are planning to filter the same way we divided Democrats and Republican data from our initial primary result data set. So this is what you have done. So you know that is stored in df facts. So we are putting a filter in df facts where candidate is equal to Hillary Clinton. So that will be stored in HC, and the data of Bernie Sanders will be stored in BS. So after that, what we are doing is that we are doing a one-hot encoding. So we'll add two more columns in our data set, a WBS and WHC. In this case, we are going to do one-hot encoding, and what we're going to do is that we are going to include, or we are going to attach two more columns in winner facts as WHC and WBS. So it'll just contain either 1 or 0. And so you can edit it in that way, whichever county. So if you're considering a county, let's say Artuga County, say if Hillary Clinton is the winner, it will have a 1 in WHC, and in WBS, it will have 0. Similarly, in which counties Bernie Sanders won, so Bernie Sanders will have 1, so WBS will have 1, and WHC will have a 0. And then we are creating different views for both of these two together. So this will only tell me wherever WHC is 1. That means this will only show me the counties where Hillary Clinton won. This will only show me the counties where Bernie Sanders won. And we are creating a view for both of these. So for Bernie Sanders, the view is WBS, and for Hillary Clinton, it's WHC. Then finally, we are merging both of them together using union. So select all from WHC, union all select from WBS, and finally, you have stored it in result, and we have created a table view known as result. So let me show you what this result contains. So there it is for Artuga. It was Hillary Clinton. So we've got the Bernie Sanders data over here at the bottom, and I've got all the different fields also from my second data set, the different features that I chose from my second data set to analyze it. So now comes the actual analyzing part. This is where we are going to perform k-means, but first we have to define the feature columns. Actually, you have to define what is the input that you're going to feed so that you get an output. So this is actually the input that you are going to feed to the machine so that the machine learning goes on, and finally it gives you some kind of result, right? So this is where I'm defining. Again, I'm using an array to define all the different fields from my data set. So I'm using person 65 years and older, female person percentage, white alone or black or African, American alone, Asian alone, Hispanic or Latino, foreign-born persons, language other than English, spoken at home, bachelor degree or higher, veterans, home ownership rate, median household income, persons below poverty level, and population per square mile, WHC and WBS. And then I'm going to use the vector assembler. So this is what enables different machine learning algorithms where we are using k-means. So my input column is features calls. So this is going to be the input, and my output column and will be called features. So whatever result that I'm going to get is features, and we have to transform the results. So this is the final table view that we have created, and you know what transforming means, or transforming again means. So in our strategy, we already saw that we have to transform the data first. So my updated data set was results. So I'm going to transform result and put columns as going to be these, which is feature columns. And output table view will be called features. And then we're going to perform the k-means clustering, and we're going to store it in a variable called k-means. So we're using different functions from Spark library, and we have chosen Spark with clustering k-means. And you know that in k-means we already defined that how many clusters do we need, and we need 4. So we have selected 4 clusters, and then we are going to set feature columns as features. And then set prediction column as predictions. So after that we're going to make a model, and we have defined our input and output columns in rows, so we're going to use keens.fitRow, and whatever predictions we will get we're going to store it in a model, and then we are going to do this, and that we are going to print the cluster centers for each cluster. So let me show you what my cluster centers are. So after we run this code, you can see that these are the different cluster centers. So just what I can make you understand about what we're going to do after k-means clustering and how to analyze it. So the numbers are present. They are placed very haphazardly. So what I have done is that I've picked out each of the cluster center points, and then I have made a new table. Yes, so this is it. So you know that we have 4 clusters. We have got the 0th cluster, first cluster, second cluster, and third. So 0, 1, 2, 3. Okay, so 4 clusters, and we have found out this cluster centers according to different features that we fed into my k-means algorithm. So what we observed here in WHC and WBS is that the winning percentage, or the winning chances, of Hillary Clinton was 0.9, whereas winning chances for Bernie Sanders was 0.1. And then if you observe the differences in the cluster centers for each feature, here you can see that there is not much difference, not even here. So it's 50, 49, 49, 51, and then it's, well, again, it is not much of a difference, but if you see here that it's 9 and it's going to 16. So you can do a more detailed analysis on Black or African American. So if you want to know the real support of Black or African American, and you want to see what was their voting pattern, or how popular was Hillary Clinton among them, so maybe this could be a good field to analyze because you see the variations in the number. Similarly, you can check out other features, and you can check out here at 16, 8, 9, and 36. So maybe, again, Hispanic or Latino field, and you should do some more analysis on it. And even here you can see in veterans there's 47,806, whereas we've got 182,000 all. So there is also a lot of difference. And here is only 2,759, and we've got in the 10,000s, we've got numbers, and even 100,000s here. So this is how we can identify that, which are the fields or which we can find the main reasons of the main points where you should make your analysis. So let's go back to our Zeppelin notebook, and here it is. So now what we're going to do is that we're going to visualize the result first. So we are counting from predictions. So you can see that in cluster 1s, the prediction means prediction contains my cluster. Since you know that I've stored my clusters, my cluster information and prediction, this is my output after k-means. So I've got this many clusters. So this is the count of my counties, or a count of different various that lie in my particular cluster. You can see that in cluster 1, I have got 1,917. In cluster 2, I've got 751. So maybe I should pay more attention on analyzing cluster 1, right? So that's why I've selected cluster 1 here, and we're making different predictions. So you can see that in the x-axis, I have got foreign-born people, and in y-axis, I have chosen language other than English spoken at home. And then we are grouping it by candidate. So you can see the lighter blue is for Bernie Sanders and the more dark blue is for Hillary Clinton. So all this light blue is for Bernie Sanders, and you can see that as the number of foreign people increases, you can only see Hillary Clinton in the scatter plot here. So there might be a few outliers, like back here in the sizes defined according to Black or African American alone. So you remember that this was the feature where we find a lot of variations in the numbers, so that's why we grouped it according to that. And you can see the bigger the circle represents, the more Black or African American alone. And that's what the conclusion we can find out from this scatter plot. And we can see that as the number of foreign people increases, the popularity of Hillary Clinton is more in larger groups of foreign people. You can also choose different parameters out of all the different features that you have chosen. So remember that we have also seen the variation in veterans. So let's choose veterans in a y-axis. So let's also change x-axis, and let me just use white alone here. So you can see here that there is the x-axis that has white alone, and this is the veterans. So you can see that Hillary Clinton is popular among veterans, also in a smaller group of veterans. Since we have decided the size in Black or African American alone, so the size also represents some values. She is popular among the African American veterans. And then as you go ahead and as the count increases, you can see actually, since it's a scatter plot, and it almost represents that this is a point as the number of people increases, or as the number of white people increases, the votes are equally kind of distributed between Bernie Sanders and Hillary Clinton, because there are a lot of points in this scatter plot over here. And you can go ahead and drag and drop different features, and you can make different visualizations on that. Now what we've done is that we know that there are 1,917 counties in my cluster 1. So I'm going to do is that I'm going to see that among these 1917, how many were in favor for Hillary Clinton and how many were in favor for Bernie Sanders. So in cluster number 1, you can see clearly Hillary Clinton is the winner and Bernie Sanders only has got 764, whereas she got 1,153. Similarly, in cluster 3, again, Hillary Clinton is the winner with 9 and Bernie Sanders with 1. Then it 2, she's also got 388 and Bernie Sanders was 363. So this was a very close call. And again, in 0, you've got 119 and 30. And then we went ahead and created a line chart also of the word distribution for Hillary Clinton and Bernie Sanders. So in keys, we have selected prediction. The values here are WHC and WBS, the sum that we have got over here. So definitely Bernie Sanders is lagging behind. So even though you don't have that table for you, you can also find it out according to this line chart. So you can see that in cluster 0, even again, Hillary Clinton was ahead of Bernie Sanders. In cluster 2, there was a very neck-to-neck competition, and you can see it in the graph year. So this represents cluster 2, and so you can see you have a neck-to-neck competition. And again, in cluster 3, they have got neck-to-neck competition. So this describes the distribution of votes for Hillary Clinton and Bernie Sanders, and definitely Hillary Clinton knows ahead, and that's why, of course, she won the primary elections. So again, you can go ahead and we have created the same graph. It's only just area graph instead of a line graph. The key here are state and candidates. So I've got states and candidates over here, and the values is counties. Once, if you just hover onto this bar chart, you can see that in Connecticut, Bernie Sanders won 115 counties. In Connecticut, Hillary Clinton won 55 only. So in Florida, Hillary Clinton is 58, and in Florida, Bernie Sanders is 9. And here you can see in the Maine, Bernie Sanders won 462. So Bernie Sanders got a majority of votes for Maine. So you can also classify it state-wise. You can find out which are the states. And as Donald Trump, now you will know that which are the states that you can target, right? So you know that in Maine, a lot of people voted for Bernie Sanders, and maybe Hillary Clinton is not popular. So you can go ahead and lead out. So as Donald Trump's party member, you can just advise him to go in Maine and carry out different campaigns because Hillary Clinton is not so popular there. So maybe it would be a little easier to get votes from the people in Maine. So this is what you can make a conclusion from, and it might not be very accurate, but this will be very close. The thing is that you can make different charts. You can make bar charts, you can make pie charts, so whatever counties won have made in the bar chart. So here it is in a pie chart. It looks better, but it's not maybe as insightful. I just placed it so that I can show you you can make pie charts also. So these are the insights that you can make after analyzing your U.S. county data. And this is what you can tell Donald Trump. These are the different suggestions that you can actually go and tell Donald Trump that she is popular among the foreign people and the people who speak different languages. She is popular among the Hispanic people, and then in Maine, she lost a lot of counties. She almost lost all of the counties in Maine. So these are different insights that you have got, and then you can tell your superior or your employer who has hired you to do that. So this is what you can present, right? So this is for a very beginner's level, and there are some more analytics that you need to do. I just showed you a few options. You can go ahead and try more in the Democrats section also. And you remember that you have to do it for the Republican Party also. Now let me see what you've learned today. So if you have any questions right now, you can just go ahead and ask me. So does anyone have any questions? All right, so AJ is telling that I want to give it a try and I ask you in the next class. Of course, AJ, you can. I'm very happy that you found it interesting and you're going to try it. So all right, thank you, AJ. And so now we will move on and find out the solution for the instant cab use case. You remember that we have got the Uber dataset, which contains the pickup time and the location by 2 columns, latitude and longitude, and we have also got the license number for a particular Uber driver. And what we have to do is that we have to find the beehive locations. That is the point where we will find the maximum pickups, and then we will also have to find out what is the peak hour of the day. So this was the entire strategy. So we've got the Uber pickup data set, and then we store the data into HDFS. We will transform the data set and make predictions by using k-means clustering on the latitude and longitude and find out the bee point or beehive point. So now let me open my other notebook, the Uber notebook. So again, the first thing that you have to do is copy the Uber dataset into your HDFS. Now we've done that before explaining to you the U.S. county analysis. So again, the code is kind of the same. The first thing is that, again, we are importing some Spark SQL packages and some Spark ML lib packages because we are going to use k-means clustering. And you can see vector assembler here again, Spark ML clustering, k-means, and other Spark SQL packages. So then we have to start our SQL context, and we're doing it the same way. Then the first thing, again, we have to define a schema. So now I don't have many fields. I've got only 4 fields if I remember. So the first field was the date and timestamp that defines the time. So we're defining it as DT. And the next field is the latitude, the longitude, and base. Then I'm going to read my data set. This is the path in my HDFS where my Uber data set is there. So I define schema as schema here. The header is true because, again, my data set contains column headers, and I'm going to store in DF. So feature calls here is going to be latitude and longitude because I'm going to find out the beehive point, the point where I will get my maximum kick up from. So again, I have set the input calls as feature calls and output calls as features. So I'm using the assembler to transform my data set, and then again I'm using k-means, and we use the same elbow method. We found out that we should make 8 clusters for this data set, okay? And then we are selecting the prediction column and the output column as predictions, and then we have printed the cluster centers for each cluster. So definitely whatever result we are going to find, the cluster centers will tell me the exact location. So this cluster centers that we will find after k-means is actually the beehive points. This will be the point where I will find maximum pickups, right? So here I have printed my cluster centers, and this defines the latitude and longitude. And this is going to be my location where I'm going to find the maximum pickups. And I got 8 results like that because I got 8 clusters and defined the 8 centers for different clusters. So this is exactly like the K-school problem that I explained to you in k-means. This is exactly what happens just as we found out the center of each cluster, and that is where we are replacing the school or building, the new school. So similarly, this is going to be my beehive point, and this is where I will place my maximum number of cabs, okay? So we found out the beehive points. The next thing we will need to do is we need to find the peak hours, because I also need to know at what time should I place my cabs in the location. So what we're doing now, we are taking a new variable called Q, and we are selecting hour from the timestamp column, and then the alias name should be hour, and we're getting it from our prediction or from the result that we got after my k-means clustering. So now we are grouping it, and it will have the different hours of the day, and then it will just show me the pickups at the different hours of the day in the location that we found out are the beehive points. And then we're going to count how many pickups we are going to get from that place, right? So we're ordering it by descending. So the smaller pickup count will be the first, and then the larger will be at the bottom. Similarly, again, we are creating a new variable called T, and we're going to do the same thing. So here what we're doing is we are selecting the time, the hour, the date, the latitude, longitude, prediction, and we filter by hour, which is not null. So we're filtering out the null values from here. So now we have created a table view for categories. So let me show you what the categories contain. Okay, let me just go down. So I've done some few operations here. So let's scroll back up and I'll show you. And again, we have created table views for T and Q also, which is again T and Q, all right? And then I have made some visualizations for each. So then we have created a value P where hour is not null. So again, we have filtered out the null hours and we have created a new view called P. So here is my hours. This is my count and in the x-axis that show how many pickups were there, and this contains different hours of the day, and then I have grouped it by prediction. So the size is according to the count. So you can see that the bigger the circle means the more pickups. So you can find out the biggest circle, and you know that you can find the biggest circle as you go along the x-axis because this is where the count increases. So you can find out the biggest circle would be here, and it lies in my fourth cluster. And you can see that there are 8,915 pickups at the 17th hour of the day, which is around 5 p.m. And so you know that the maximum pickups are around 4 o'clock or 5 o'clock, and this lies all in my fourth cluster. And so it means my peak hours are around 4 or 5 o'clock in the evening, right? So this is what insight we have gained, and you can tell Instant Cab CEO that I have found out that your cabs should be ready around 4 or 5 because that's the time when people go home from offices or they're going out for dinner or something. And this is what another table view looks like, which is T. So here we have latitude and longitude, and this is where we are finding the beehive locations. So I have got the distribution in a scatter plot again, and you can see that we have got very dense points over here. It means that these represent the beehive points. So what you can do is that you can just put the US map and scale it according to this scale over here, and then you can exactly find out what is the exact location where you need to put your cabs around the 17th hour or the 16th hour of the day, all right? And you know that we had a lot of rows, but the results are only limited by 10,000 if it's around 10,000 rows. But we obviously had a lot more, and you can check in different clusters. So now we are analyzing cluster 0. So here, if you see this point over here, this lies in cluster 4. And this lies in cluster 5, and this lies in cluster 0, so you can analyze each cluster also. So here I have just laid out the latitude and longitude for my 0th cluster, so you can see here where prediction is equal to 0, and I've selected this from the table view of T. So here you can find out the exact latitude and longitude. And here the latitude is 40.722 and the longitude is negative 73.995. So this is how you can pinpoint location where your cab should be during the peak hours. Again, if you see this distribution, this is just a pie chart that I've created with that tells you what is the count of pickups at each hour of the days, starting from 0 to 23. There are 24 slices in this circle. So you can see that these few slices are the bigger chunks, and this is the 19th hour of the day, which is around 7 o'clock, 6 o'clock, 5 o'clock, 4 o'clock, 3 o'clock, and so on. So you can see the midnight maybe nobody travels, so maybe your cabs could rest, or you don't have to place any more cabs during this part of the day. These are the insights that you gain. So any questions on that? I think after doing the U.S. county election, this was pretty easy to do, and this is also pretty easy to understand, and the results, which were also much more clear, correct? Okay, so again, let's go back to our presentation. Now let me tell you about the Edureka LMS that you have. So you will have everything in your LMS. All these classes are recorded, and they will be here in your LMS. So even during this class, if you forget something that I said, you can just take a look at this recording of the class again in your LMS. So you can just go ahead and learn on your own. You'll have all your course content yourself, base course, so whatever documents that you want related to your subject, and you will find it here. So just let me show you that. So even the entire course content is here. So whatever documents, whatever presentations, and all the recordings will be in here in the course content according to different modules. You'll also have access to different projects related to your course, and you can just download the problem statement all in the requirements that you need to do in order to do this project. You can just download it, and after solving it, you can submit it here. And again, you have the Edureka VM, so there is also a proper guideline method about how to use this VM. If you have any doubts, you can call our 24/7 support team also. Let me just show you the LMS. I just have to go to the edureka.co, so I am already signed in, and if you're not signed in, do so. There will be a sign-in option here at the right corner, and you can just sign in and then just go to courses. To my courses, there are different courses that I have brought from Edureka. So you can just go to course, and there's everything that you want to get started with Hadoop. You have got everything mentioned here, the software, the hardware requirements. Then you have got the pre-recorded sessions over here, and one class 2 you can watch anytime you want. And the best part of your LMS is that you will have a lifetime access to it. It's not like once your classes are over and once you've learned Hadoop and your batches are over that you're not attending any more classes. You can still have access to all the older classes that you attended, and you can view it anytime you want. So there is the course content. There is for Module 2, the class recording. There is the module presentation, the quiz assignments, and everything. And again, I'm telling you, if you have any doubts about how to use the LMS, you can always call our support team. So does anybody have any questions? All right. Thank you for attending this session. I hope you had a good time in learning about Hadoop and Spark. You can rate us and let us know how much you have enjoyed learning with Edureka. You can comment your experiences. You can even give some suggestions. And don't forget to like this video if it really helped you. You can also help us get some more ideas about what we should come up with next. And then you can also take part in our service so that it can improve us more. So thank you for watching this video, and I'll see you next time. Until then, happy learning.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!